Welcome to Spring LIB.
Okay, so this one's about developing film. I love these application problems. They're very interesting to me. So, okay, to expose film, to develop film, films have silver bromide, and then it's exposed if light absorbed dissociates it into its atoms. And so to dissociate, you need 1 times 10 to the 5 joules per mole. So energy 1.00 times 10 to the minus 5 joules per mole. And then we know a photon, it's just able to dissociate them. We need to get its energy in electron volts. Um, so wait, is this mole or molecule? So I'm just going to pause and make sure everything was transcribed correctly. Okay, so I was really wishfully thinking that these were transcribed incorrectly, but indeed they're not. So what we need to do is convert from mole to molecule. So if it's 1.0 10 to the 5 joules per mole, and we can say that where I had it pulled up, AgBr molar mass 187.77 grams per mole. Then we convert it to per gram. Oh no, we don't even need the molar mass actually. It's so what we want to do is multiply by divide by, I was just thinking of the units, 10.0622 10 to the 23 particles or molecules per mole. So multiplying that out gives the energy per molecule is 1 times 10 to the 5, 6.022 times 10 to the 23, and that's 1.66 10 to the minus 19 energies per particle, or joules per particle. Oh, 1.66, excuse me. I'm always double checking the calculations in the transcription process. 1.66. Great. And I'm just going to double check it again. 166, 10 to the minus 19. Wonderful. And so now I think we're better prepared to answer the questions. So it's just stable. So we know that this is the energy in joules. And so, this is perfect because this is almost, so we want to get the energy in electron volts. So for A, we just want to take this and convert it to electron volts. So we're just going to take this and divide it by 1.660 times 10 to the minus 19. And with that, I get 1.04, as I sort of expected. And what's next? We want to solve for the wavelength, and so we can set this equal to hc over lambda. E is hc over lambda, so lambda is hc over E, and I'm just going to use this E and use the SI united hc. So let me go ahead and calculate that. With that, I got 1197 nanometers. So it's IR light, huh? I'm curious if this problem will tell us why you have to develop in a dark room. Let's find out. Great. And C, we want to get the frequency. So E is HF. So F is equal to H over E over H, I should say. And so let's go ahead and do that calculation. Here's E divided by H. So do 6 times 10 to the minus 34. And then that's, oh wow, that number doesn't seem right. Oh, I left the conversion there. Great, so 2.51 times 10 to the 14 hertz. 251, 10 to the 14 hertz. Great. And for D, light from a firefly can expose the film, but the radiation from an FM station cannot. And so why is that the case? Well, 100 megahertz is just way low of an energy per photon to cause this this molecule to dissociate. You need to have the right amount of energy. Even if you have many of these photons, none of these photons are able to dissociate. And so, yeah, that's why it's unable to dissociate. Oh, and I guess we want to get the energy of the photon. So let's actually just calculate the energy of the photon to really do that. So so then E would equal H times F, and then we're going to use F is equal to, let's say 100 megahertz. So 100 times 10 to the 6. And when I do that, and I'll go ahead and convert that to electron volts as well. So H times 100 times 10 to the 6. And I want to multiply 1, 6, 10 to the minus 19. Oh no. Oof, divide. So that's that would be 4.14. I almost said nanometers because that looks like it. So it's 4.14 times 10 to the minus 7 eV, which is not enough energy. So I guess this isn't quite about developing film. It's more about exposing film. So it's just why does a Polaroid, I guess, light up when exposed to light? It's kind of surprising to me that I guess that's the fact that this, like the molecule will probably still dissociate if you use a higher energy than 1, 2